This video is the beginning of the notes for Unit 10 on intermolecular forces and phases of matter. We're specifically going to review the types of intermolecular forces that you should have learned about in the previous simulation. So when we think about particle level attractions that happen, we really can divide them into two groups. The ones you are already more familiar with are over here, the intramolecular forces, or the forces that occur within a molecule, inside of a molecule. So you, from first year chemistry and earlier this year, you know about ionic bonds, where a metal and a non-metal exchange electrons. The metal gives electrons to the non-metal, and then you end up with a metal that's a cation and a non-metal that's an anion, and those opposite charges attract. We've also talked about metallic bonds. And in a metallic bond, you have metal atoms. It could be the same metal atoms. It could be a couple different types of atoms. But because all metals have a weak hold on their valence electrons, the valence metals are held together by this kind of sharing of electrons. It's sometimes referred to as a sea of electrons. Those valence electrons can very easily float from one metal atom to the neighboring metal atom. But it's not like they stay in one metal atom, like they completely transfer to one atom. Like as one electron moves out of an atom, probably another one's going to move in from another atom. And we also know about covalent bonds, and those are between several nonmetal atoms. And in covalent bonds, valence electrons are shared between two atoms. Now, the new concept that you're just learning about is the fact that this doesn't apply so much as ionic bonds and metallic bonds. Ionic bonds are repeating. You've got this structure, this pattern when we're talking about ionic bonds where you make a formula unit. It's very organized. So maybe you have a couple different atoms here, and they're organized in this pattern of sorts. And they're all charged, so maybe this is the negative charge, and maybe these are the positive charges, but those oppositely charged atoms are holding each other together. When we're talking about metallic bonds, it's also really a repeating structure. We'll look at it a little bit more later in the chapter, but so you've got a whole bunch of like copper atoms all in a row. It's a very, again, an organized structure that repeats on and on and on and on. In covalent bonds, it's not this repeating structure. You make molecules. So we can have, for example, the H2O molecule. Hydrogen's really big. So you got an H2O molecule, and there's a lot of these little H2O groups. So in a covalent bond, everything's bonded in little groups rather than repeating patterns. But we know that covalent compounds also can be liquids and solids, so there must be something that holds one little molecule of water to another little molecule of water. The thing that holds covalently bonded molecules to other covalently bonded molecules are what we're learning about now, intermolecular forces, forces between molecules. So inter means between, where intra means within the same molecule or between several different molecules. So we're going to learn about London dispersion forces, dipole-dipole attractions, dipole-induced dipole attractions, and hydrogen bonds. The first type of intermolecular force, the first type of force that holds one molecule to a second nearby molecule, is called a London dispersion force. A London dispersion force is it's temporary. It's a temporary attraction when two nearby molecules have temporary dipoles. It can be present between any two molecules, so every substance that contains covalently bonded molecules can have these temporary London dispersion force attractions between two of its molecules. And it's stronger between molecules with an electron cloud that is what we say more polarizable. So let's talk about why London dispersion forces happen. If you look at these three pictures here, electrons, which I'm kind of highlighting here in the frame 1, and here's the electrons in frame 2, here's the electrons in frame 3. Electrons, they're constantly whizzing around inside the atom all over the place. And so, just purely based on chance, sometimes they'll be one on one side, one on the other. Sometimes they'll be completely opposite each other. But there will come times, as these electrons are whizzing through the electron cloud, where they randomly happen to both be on the same side of the atom. And when that happens, you get a temporary, short-lived dipole, or that means that this atom, for a little bit, it has a slightly negative side. So over here on the side of the atom where the electrons are, that's temporarily negative. And on this side of the atom, where the closer to the nucleus, or where there's a lack of electrons, that side of the atom is temporarily positive. And this just happens because electrons are always moving, they're never sitting still. Sometimes they end up in different spots. So that's happening all the time in every molecule. Now what happens if one molecule happens to get its electrons on one side, so it gets a temporary dipole. It's got a negative side and a positive side. There's going to be another atom or molecule nearby. And so when this molecule gets a temporary dipole, it becomes polarized for a minute, has two sides, negative and positive, it can induce or cause a nearby another molecule to become polar. So the electrons, because this side of the first atom is positive, now it causes a neighbor, pulls its electrons from a neighboring atom a little bit over to this side of the second atom. So this atom gets a temporary dipole, and then once you have a positive side here and a negative side here, an attraction forms between these two atoms. That attraction is known as a London dispersion force, and that can happen. Here we've got a third atom that's had a temporary dipole induced on it. So London dispersion forces can have a wide range of strengths, but the more polarizable that an electron cloud is, the stronger the London dispersion forces are. Things that make an electron cloud more polarizable would be longer atoms, because a longer atom would allow, or not longer atom, longer molecule, because a longer molecule is going to allow the electrons to separate more, so you get more charge separation. That's going to be a stronger, more polar molecule, even though it's temporary, because it can get more charge separation. You also, if an electron or an atom has more electrons, that's also going to be a more polarizable atom, because the more electrons that you have, the more electrons that you can get to move to one side of an atom versus the other side. So like if you only have 2 electrons, it's only 2 electrons worth of charge that can act like happenstance shift to one side. But if you've got an atom that has like 50 electrons, there's more electrons that can shift to one side or the other. Anything that can make the difference between the positive and negative side more dramatic, that's going to have stronger London dispersion forces. The second type of attraction that you can have between two molecules is called a dipole-dipole attraction. Dipole-dipole attractions are a little bit different because we're talking about something that's more permanent, where London dispersion forces, like they're always there, but like molecule 1 and molecule 2 aren't always reacting or interacting with one another. It's random, it doesn't happen all the time. Where dipole-dipole is more permanent. You have 2 molecules that are permanently polar, that permanently have a positive and negative side because of their geometry and the differences in electronegativity of the atoms. So when you have the cause of dipole-dipole attractions is 2 polar molecules, and what happens is the positive side of the first molecule can form an attraction to the negative side of a second molecule. So that dipole's always there, it doesn't just happen by like happenstance. We've got a molecule here, and if you look in the first picture, you can tell just from this space filling model that this is not in this direction, it's not symmetric. We've got an oxygen over here, and that oxygen is more electronegative. Over here we've got carbons and hydrogens that are less electronegative, and so electrons in that molecule are going to be shifting this direction. So one way to show a dipole is with these little Greek lowercase deltas. This indicates negative side, this indicates positive side of the molecule, but this little arrow is a second way to show that this molecule has a dipole, that it has a positive and negative side. Both of these molecules are polar. They both have a positive and negative side, so the dipole-dipole attraction is happening right here where this negative side of the first molecule attracts the positive side of the second molecule. This is a different picture of the same thing. It's called an electrostatic potential map, and what you're seeing is this red area is where it's more electron rich, and the blue area is more electron poor, or more of a positive side. And so you can see the negative side of this molecule attracts the positive side of this molecule. The third type of attraction that holds molecules to one another is called a hydrogen bond. Hydrogen bonds are present between, they're a very special case actually of dipole-dipole attractions that only happen in certain circumstances and that are like exceptionally strong. A hydrogen bond is between a hydrogen on one molecule, and that molecule within that molecule has to have either an HF bond, an HN bond, or an HO bond, and the F, N, or O atom on a second molecule. So the hydrogen bond is not the bond between the HF, the HN, or the HO. That's a covalent bond. But if we look at these molecules here, in this molecule there's a bond between H and O, and in this molecule there's a covalent bond between H and O. These HO covalent bonds are very exceptionally polar bonds because oxygen has a very high electronegativity and hydrogen has a weak attraction for its electrons, so the electrons spend more time in the oxygen, making this bond have a negative side at the oxygen and a positive side on the hydrogen side. So the hydrogen on the first molecule can form a fairly strong attraction to the oxygen on the second molecule. It's not a covalent bond, but it's still similar. It's an attraction, electrostatic attraction between the positive side, the H, in one molecule and the negative side, the O, in another molecule. And as I said here, I know the name is called hydrogen bond, but it is not a chemical bond. When we say chemical bond, we usually mean covalent bond, ionic bond, or metallic bond, which all three are stronger than any of these intermolecular forces that we're talking about. A hydrogen bond is not a true chemical bond, but it is called a hydrogen bond, so you should know it by that name. So I just wrote down what I'd already said. This really is a special case of a dipole-dipole attraction. We've got polar bonds, the HF, HN, and HO bond, but they're all especially polar because F, N, and O are especially electronegative atoms. So because these bonds are more polar than other covalent bonds, the attraction between the hydrogen on one molecule and the oxygen, nitrogen, or fluorine on the second molecule is especially strong. And so because these dipole-dipole attractions are extra strong, they are given their own name and they're considered a special case. So it's hydrogen bonds are stronger than your run-of-the-mill dipole-dipole attractions. The last type of intermolecular force that we will talk about are called ion dipole attractions. Ion dipole attractions are present between ions and polar molecules, and we most especially see this when ionic compounds are dissolved in something polar, which often, not always, but often is going to be water. And so the cause of this is that you get the anion, which is negative, attracts the positive side of the polar molecule, on the other hand, the cation, which is the positive ion, attracts the negative side of the polar molecule. So it works a lot like all the other intermolecular forces that we've been talking about. So this picture here is a good illustration. We have the classic example is water dissolving any kind of salt, and the classic salt is NaCl. So notice we've got the anion here, and all the waters are orienting their polar, and they're orienting their positive sides towards the chlorine. And over here we have a sodium, and sodium is all the water molecules are orienting their negative side towards the sodium. So those are the 4 intermolecular forces that we're going to talk about. Keep in mind, all of these intermolecular forces vary in strength, but they are all much weaker than an ionic bond, a covalent bond, or a metallic bond. So it takes less energy to break an intermolecular force attraction than it does to break an actual chemical bond. And that's why these are not considered chemical bonds, but a weaker classification of attraction.